Hi, Year 11. Let's carry on with question 21. 4 cups A, B, C and D contain hot coffee. Which cup contains the coffee warm the longest? So we know that we want the least amount of heat transfer from the coffee to the surroundings. So we need to think about the worst heat transfer surfaces. And we should hopefully remember that white is very good at reflecting but very bad at transmitting and absorbing and emitting. So we want to choose white for the outside surface of the cup so that the heat is reflected back inside of the coffee but not transferred through as easily. And then we also want to prevent convection currents of water vapour, of steam coming off the coffee, which remove heat with the steam. So we pop a lid on so that any water vapour can then condense and move back into the coffee, so that we prevent the heat transfer that way. So that was C. In 22, 4 students are asked to state and explain the relative magnitudes of the thermal expansion of solids and gases. So if you are asked about relative magnitudes, you're comparing one to the other, and then magnitude means the size. So compare the size of the thermal expansion of solids and gases. Which student is correct? So the correct answer is B. Gases expand more than solids because the attractive forces between molecules are much weaker in gases. So what you have to remember is in solids you've got these really strong forces of attraction, they're bonds between the particles, so that if they were to gain kinetic energy and vibrate more, they can't really move into a much larger space. The thermal expansion is minimal, whereas with a gas, the molecules don't really have bonds, there's no force of attraction, and so when they gain their kinetic energy, they are free to move and take that space. So that is B. In 23, which statements about evaporation of water are correct? So evaporation causes the remaining liquid to cool. Yes, so in evaporation, you have the most energetic particles at the surface of the liquid, escaping the surface and converting from liquid to gas, so leave as water vapour. They take energy with them, which means that the average kinetic energy of the particles left behind in the liquid is now lower, which means that the temperature is now lower. So that is true. During evaporation, the more energetic particles escape from the surface of the liquid. Well, I just used that to explain number 1, so yes, that is also true. And then number 3, evaporation only happens at 100 degrees Celsius. No, this is boiling. So at 100 degrees Celsius, we have the maximum rate of conversion from liquid to gas. That's boiling, but we can have change from liquid to gas at a slower rate, so less particles per second changing their state, and that can happen at any temperature, and that's where we have evaporation. So in 24, there we go. The pressure of a fixed mass of gas in a cylinder is measured. The volume of the gas in the cylinder is slowly decreased. The temperature of the gas does not change. Which graph shows how the pressure of the gas changes during this process? Okay, so I just sketched it out for you. So we've got the volume is getting smaller. The number of particles of gas hasn't changed, and so the particles now on average are going to be closer together. There's more in a tightly packed space. The temperature does not change, so that tells us that the average kinetic energy of the particles also doesn't change. Okay, so we know then that the pressure could never have been 0 to begin with, because the temperature originally is the same as the temperature afterwards, and you weren't at absolute 0, so therefore you weren't going to have 0 pressure. You had some average kinetic energy of the particles, so you would have some collisions. So because of that, you would never have no pressure, so B is a no. We can get rid of A. The pressure is not going to stay the same. We know this because if there are now more particles packed into a tighter space, you're going to have more collisions in a smaller surface area, and pressure is force divided by area. If there are more collisions in that same area, the force increases, which means that the pressure of the gas is going to increase. In 25, a fixed mass of gas is trapped in a container. The temperature of the gas is increased, but the volume of the gas is kept constant. So I said temperature increases, volume stays the same. Pressure is force over area. How does this change affect the average kinetic energy of the molecules and the pressure on the walls of the container? Well, firstly, you need to just remember the definition of temperature. It's a measure of the average kinetic energy of the particles. So if the temperature has increased, so has the average kinetic energy of the particles. That's A or C. But we also know that if the volume stays the same and the particles now have more kinetic energy, they are going to collide with the walls more often. So there's going to be more overall force on the same area, and so the pressure also increases. Gives you A. In 26, 4 metal blocks at a temperature of 200 degrees Celsius are left to cool down to the same temperature. So the change in temperature is the same for all metal blocks. The table gives the mass of each block and the energy it transfers to the surroundings as it cools. Which 2 blocks are made of the same metal? So we can identify the metals by their specific heat capacity values. And we know that if we have the same metal, they have to have the same specific heat capacity value. So we take our specific heat capacity equation here. C is E over m delta T. We know that delta T is going to be the same for all 4 blocks. And so the dividing by delta T has the same effect on all of them. So we can ignore that and just look at a proportionality statement and say that C, the specific heat capacity, is proportional to E over m. So the higher the value of E divided by m, the higher the value of C. So all I've done in each case is I've divided the energy by the mass and listed it here. And you can see that it's the same for 1 and 3, so they have to have the same specific heat capacity value. Okay. In 27, 4 cubic copper containers are filled with water. The surfaces of all the containers are painted black. 2 of the containers have sides of length 20 centimetres, and the other 2 containers have sides of length 40 centimetres. 2 of the containers contain water at 80 degrees Celsius and the other 2 at 30 degrees Celsius. Which container radiates energy at the lowest rate? Okay, so firstly, the larger the surface area, the more space there will be for heat to transfer. So C and D will be transferring at higher rates than A and B. And we want the lowest rate, so we know we're going to choose either A or B. We also hopefully remember from our cooling practicals with hot water that the cooling happens quicker at higher temperatures, and so we want to choose the lower temperature, so that would be A. In 28, a glass contains an iced drink on a warm and humid day. They're telling you humid because it tells you then that there's lots of water vapour in the air. Water starts to form on the outside of the glass. So what that means is water vapour around the cup is cooling and turning to liquid on the surface. And so that's condensation. What is the name of the effect by which the water forms? That's just condensation, you need to know that. In 29, the diagram shows a convection current caused by a piece of ice placed in a beaker of water at room temperature. Which row correctly compares the temperatures and densities at water points P and Q? So P is at the bottom, Q is at the top. So ice is absorbing heat from the water so that it can melt, which leaves the water at the top at a lower temperature while it is absorbed by the ice in that local region. Okay, so particles then near the ice will be vibrating less because they've got colder and they become more dense. When they become more dense, they then sink, and so the cold water sinks to the bottom. The hot water is pushed up to the top. Okay, so the temperature at P is lower than the temperature at Q, which means that the density at P is higher than at Q. The cold, more dense water sinks to the bottom. That's also one to just remember, really. In 30, a ship sounds its horn when it is 790 metres away from a cliff. A passenger on the ship hears the echo 4.8 seconds later. What is the speed of sound? Okay, well, you're just using speed as distance divided by time. But to find the total distance that's travelled, the sound has to leave the ship, bounce off the cliff, and return back. So it does double the distance between the two. So that's 790 times 2. And then you divide that by the time, and you get 329, which to 2 sig figs is 330. So that gets you B. In 31, a drop of water from a tap falls onto a surface. That's a weird thing. Don't know what that is, sorry. Exam has printed weirdly. Onto the surface of some water of constant depth, I would imagine. So we can see view, and that's probably from above. So we're looking down at the drop of water, and we can see the wave fronts are radial. So remember that what that means, that in all directions you've got waves travelling out away from the source. We hopefully remember that water waves are transverse, okay? So the energy transfers across, but the water moves up and down. And you should also hopefully remember then that they're all going to travel at the same speed. So that's C. That's one that we talked about and just one to remember, really. In 32, the diagram shows a wave. What are the amplitude and the wavelength of this wave? Amplitude is just the maximum distance from the rest position, so that's 3. And the wavelength is just the distance from peak to peak, and that's 8. Again, if you don't remember the definitions, you won't be able to do this, but that's the only way to get it. In 33, let me see if I can squeeze it all in. Visible light has wavelengths in the range 4 times 10 to the minus 7 and 7 times 10 to the minus 7 metres. It's visible light, which is a clue because it tells you that the speed of light has to be that of all of the things in the electromagnetic spectrum, 3 times 10 to the 8 metres per second. What are the range of the frequencies of the visible light? So we have an equation linking frequency to wavelength, V equals F times lambda. F is V divided by lambda, which V in this case is C. So I can work out the frequency value for both wavelengths. So you can see that I've done that here, and this then will be your range. Okay, so you can see that this rounds to 4.3 times 10 to the 14 to 2 significant figures, and then 7.5, so that gets you D. In 34, again, this is one that you just have to remember. Amplitude is maximum displacement from rest, so you need the tallest waveform. And frequency is the number of waves passing a point per second. So in the same amount of time, I need to see more waves. So that gets me the one that's squished up as much as possible, gives me A. In 35, a sound wave travels from air into water. Which row describes what happens to the frequency and the wavelength of the wave? So what I need you to remember is that the source of the wave, so whatever's producing the sound, hasn't changed. So it's emitting the same number of waves per second, which means that the number of waves per second in air hits the water boundary at the same frequency. So waves will enter the water at exactly the same frequency. Frequency stays the same. The source has to change for the frequency to change in all cases. So C or D. We know. Now, this is where you could have got caught out. Water is more dense than air. So that means that light will be slower in it. But what you need to remember is that sound requires particles to travel. It's the collisions of the particles that causes the sound to transfer. So if the particles are more dense and closer together, the collisions can pass on quicker. And so they're going to be travelling more quickly in sound. So as soon as you reach sound, you can tell it's early in the morning here. As soon as you reach the water, so the wave is coming in, and as soon as it hits that boundary, it's speeding up, which means that that crest gets further ahead than the one behind it, which pulls the crests apart, and it increases the wavelength, which gives you D. Almost there. So 5 more to 36. Which statement describes monochromatic light? Mono meaning one, chrome meaning colour. So we need one specific wavelength and frequency on the spectrum to provide one colour. So therefore you need to pick A. It's just light of a single frequency. Now in 37 it says, which diagram shows the dispersion of white light by a glass prism? So what I need you to remember firstly is the order of the rainbow. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And this tells you the relative magnitude of refraction of the light of that colour. So you can see that red refracts the least and violet refracts the most. Okay, if you literally draw your rainbow down, it kind of shows you where you should expect to see things. Refraction will occur at each boundary. So as soon as the ray hits the prism, there'll be refraction there, so the light changes direction. And then again, once it reaches the other side and it goes from the prism back to air, it refracts a second time. So we should expect to see refraction happen twice, so bending twice. Okay. Now we know that red is affected by refraction less than violet, so we should expect to see the bend for the violet light to be more extreme than the red. So we can't choose C or D because the red and the violet have come out parallel. That doesn't make sense if one gets bent more than the other. Okay, and then we choose between A and B and we see, well, actually, there should have been some difference in refraction for red and violet inside of the prism too, and so it can't be A. In 38, an object O is placed at point P near to a thin converging lens. The diagram shows 3 rays from the top of O passing through the lens. Each point F is 1 focal length from the centre of the lens. Each point 2F is 2 focal lengths from the centre of the lens. The object O is moved to point Q on the diagram. Now, I've actually drawn this arrow in. It's hard to tell because of the lighting, but it's actually green. I would just draw it. Make your life easy and don't have to try and remember and visualise in your head. So I moved the object to Q, kept it the same height. The same rules apply. Going in parallel comes out through the focal point. Going in through the centre carries on. You can see the new image is still inverted and it's enlarged compared to the object. It's bigger than the object. So this length is larger than this one. So that gets you B. Excuse me. Okay, in 39. The diagram shows a ray of light entering a glass block. Now, they've been very sneaky here. They've labelled the angles and expected you to realise that this 50 is not the angle of incidence. The angle of incidence is the angle between the ray and the normal line. So this is actually 40 because a normal makes right angles with the boundary. So we know that the whole thing's 90. That therefore has to be 40. We know that the refractive index for air is 1. So we know we can say n1 sine theta 1 is n2 sine theta 2. That's Snell's law. Air was 1, so this disappears from the equation, so we can get rid of that. So we can say sine 40 is equal to n of the glass, refractive index of the glass, multiplied by sine 25. And then I'm just dividing both sides by sine 25 to get n glass by itself, and that gets me A. That would catch a lot of students out. Last but not least, a tricky one to end on. The diagram shows 2 sets of wavefronts in a ripple tank. Okay, so we've got the waves coming in. These are wave fronts, these black lines. So I've drawn the direction of the wave in pink for the first one and blue for the second one. I've drawn the normal line to the boundary with a turquoise dotted line, so you can see that. Okay, a barrier is going to reflect waves. Water can't get through a barrier. Okay, so we will get some reflection. All we've done is we've put a little platform inside of the water so that the depth of the water is less. So if I look at it from a side profile point of view, if this is the container, the water originally had a depth of this, but then what we did is we placed a barrier in, and so the depth got smaller. Okay, now we know, because I told you to memorise, that shallow water is slower water. Okay, so when water is entering a slower medium, it bends towards the normal, and so the water wave direction will change. Okay, and so I've drawn the normal, I've bent it in towards, so you can see I've then drawn the direction that the waves and the wave fronts will be travelling inside of the shallow bit. Okay, a student makes two statements about the waves. When the waves reflect from the barrier, the direction changes, but the wavelength remains the same. Right, correct, it does reflect. The wavelength will stay the same because the speed and the frequency of the wave hasn't changed. Okay, the frequency is just the frequency of the source. The frequency that it hits the barrier will be the frequency that it leaves the barrier. The depth of the water hasn't changed, so it will be at the same speed, so the wavelength will be the same. Number 2, when the waves refract as they enter the shallow water, the direction remains the same, but the wavelength changes. Well, no, we've just proved that the direction does not remain the same. When it's slower, it tends towards the normal, it bends, okay? The wavelength has to change. This is because we know that the frequency has to stay the same. The frequency hitting is the frequency entering, so that's fine. The number of waves passing the point per second is the same. But we've just said that water is slower and V is equal to F lambda. So if V drops, lambda also has to drop. The wavelength has to decrease, so the waves get closer together here. So only one is true.